Anyone who regularly travels on commercial flights has almost certainly noticed a rather peculiar sensation shortly after lifting off. The engines roar with immense power along the runway, the nose pitches up, and yet, within moments of entering the air, the acoustic volume drops dramatically as the engines seem to lose thrust. For anxious travelers, this sudden reduction in engine output can feel deeply alarming, particularly because it takes place while the plane is still climbing and remains quite close to the terrain below. This script explores the exact reasons why flight crews deliberately ease back on the throttles right after leaving the ground, how modern passenger jets rarely require full engine capabilities to begin with, and how this standard practice actually boosts fuel efficiency, minimizes engine degradation, and preserves flight safety. An incredibly widespread misconception regarding commercial aviation is the belief that jetliners always use every ounce of available power to claw their way into the sky. While absolute maximum thrust capability is always accessible when environmental factors dictate it, the truth of the matter is that the vast majority of commercial departures do not require full power under standard operating conditions. Instead of expending that extra performance margin for no reason, flight crews frequently cut back on their available thrust before they ever release the brakes. This strategy is referred to in the industry as a reduced thrust takeoff, and air carriers heavily favor it because running power plants at lower internal temperatures and reduced physical stress significantly curtails mechanical wear over time. Given that jet engines rank among the single most expensive investments on a commercial jet, extending their operational lifespan provides massive financial advantages to airlines managing hundreds of aircraft. Flight crews typically utilize two primary techniques to scale back engine output for departure. The first approach is referred to as a derated takeoff, while the alternative relies on what aviators call an assumed temperature or flex temperature calculation. Utilizing a derated takeoff means explicitly choosing a lower, legally certified engine thrust rating prior to heading out to the runway. The jetliner still accelerates with complete safety and satisfies every single regulatory climb gradient, but the power plants are subjected to far less thermal strain. The second strategy is even more widespread across the flight decks of modern airliners, where pilots input an artificial, assumed outside temperature into the flight management computer that sits far higher than the actual real-world ambient reading. Since jet engines naturally produce less total thrust in thin, hot air, the onboard computer establishes a lower target power setting tailored to that simulated heat. The entire sequence is thoroughly calculated and managed, guaranteeing that the jet meets every necessary safety benchmark. This method works beautifully because departure computations meticulously weigh runway distance, total aircraft weight, local weather, surrounding terrain obstacles, and climb physics. If a healthy performance buffer exists, there is simply no logistical reason to subject the engines to brutal and unnecessary stress. Crucially, maximum emergency power remains instantly available at all times. If the crew encounters sudden wind shear, unexpected performance degradation, or any other flight deck emergency during the climb, shoving the thrust levers completely forward instantly commands absolute maximum takeoff power. The foundational reason commercial airlines adopt reduced thrust departures is incredibly straightforward. Engines simply live longer when they are not constantly pushed to their absolute limits. Jet engines operate within extraordinarily hostile environments, experiencing internal temperatures that skyrocket during high-power segments. The single hottest and most physically punishing moments in an engine's operational life cycle generally happen during the initial takeoff roll, especially on long-haul international flights where the aircraft is loaded down to its maximum structural weight. Even minor reductions in thrust can yield massive decreases in thermal fatigue. Industry data demonstrates that scaling back takeoff power by just a tiny percentage can exponentially extend engine longevity because those final, highest increments of exhaust gas temperature inflict a disproportionate amount of damage on internal turbine blades and components. This reality is a massive priority for airlines because engine overhauls are staggeringly expensive, with modern power plants built by industry giants like General Electric and Rolls-Royce costing tens of millions of dollars and demanding recurrent maintenance turnarounds that require highly specialized engineering and replacement parts. The core operational logic is therefore undeniable. If an airliner only needs a specific percentage of its total muscle to depart safely, utilizing maximum power every single time makes very little sense. Airlines protect their primary assets whenever the runway conditions and aircraft weight permit it. While setting reduced power before the rollout is an essential element of flight, the specific acoustic drop that passengers actually hear inside the cabin happens once the jetliner is already flying. Upon climbing through a specific, legally mandated altitude, the pilots intentionally pull back the power as part of a highly disciplined, worldwide protocol known as a noise abatement departure procedure. These specific flight profiles exist because neighborhoods surrounding major metropolitan airports have dealt with the pounding roar of low-flying aircraft for decades. Large, high-bypass turbofans running at full takeoff thrust produce an immense amount of noise, particularly when planes hang low over populated areas right after departure. To mitigate this noise footprint, international aviation organizations formulated standardized climb structures that carefully balance raw aircraft performance, passenger safety, and environmental noise limits. Following these guidelines, flight crews pull back the power at a specific height after leaving the ground, generally between 800 and 3,000 feet above the runway's surface. The physical transition is unmistakable to anyone sitting in the cabin. The roar of the engine softens, forward acceleration often decreases for a moment, and passengers occasionally get the false impression that the plane is leveling off entirely, even though it is actually continuing to climb steadily away from the airport. International civil aviation frameworks outline two distinct noise abatement departure paths that are utilized by flight crews all over the globe. These profiles are universally known as NADP-1 and NADP-2. And each is optimized for a specific scenario depending on the layout of the airport's surrounding communities. The NADP-1 profile is specifically engineered to alleviate noise pollution for neighborhoods situated immediately adjacent to the airport boundary. Under this specific climb structure, the aircraft maintains its steep initial takeoff posture for a longer duration after leaving the ground. Once the thrust is reduced at the targeted altitude, the jetliner continues climbing out at a relatively conservative forward speed until it crosses roughly 3,000 feet, after which it finally accelerates to clean up the wings and retract the remaining flaps. This sequence keeps the aircraft much higher in the sky over nearby homes because the slower forward speed prioritizes rapid altitude gain over pure horizontal acceleration. Gateways that feature packed housing developments right at the end of the runway will almost always mandate this specific profile. Conversely, NADP-2 functions in the exact opposite manner. Under this technique, the thrust reduction, horizontal acceleration, and flap retraction sequence all kick off much lower to the ground, typically around 800 feet above the runway elevation. The jetliner picks up speed much sooner, transitioning rapidly into an aerodynamically clean, high-speed climb. This specific method offers the greatest benefit to residential communities located further away from the airport boundary, because the aircraft achieves higher forward speeds and optimal aerodynamic efficiency much earlier in the departure sequence. Individual airports select their mandated profiles based on a combination of local topography, surrounding terrain, population density, and strict municipal environmental rules. No matter which specific noise abatement profile a flight crew executes, strict aviation regulations explicitly forbid any thrust reductions below clear minimum altitude floors. Absolute flight safety will always override any local noise complaints, and pilots must maintain a robust envelope of aerodynamic performance throughout the entire departure phase. Furthermore, airlines dictate that all noise abatement profiles are immediately abandoned during any mechanical emergencies or abnormal flight conditions. If a power plant fails, if severe wind shear is suspected, or if localized weather patterns take a sudden turn for the worse, the pilots instantly focus 100% of their attention on pure aircraft performance and aerodynamic handling, completely ignoring any local noise reduction targets. Even though these reduced thrust methods are completely routine across the global airline industry, their execution relies heavily on flawless data calculations and seamless crew coordination. Pilots calculate their takeoff metrics utilizing sophisticated software and real-time operational data that meticulously process total runway availability, ambient temperatures, wind vectors, airport barometric pressure, current aircraft weight, and critical obstacle clearance paths. The final readouts establish the precise minimum amount of thrust required to get airborne safely, with a built-in safety margin that guarantees the aircraft can continue climbing even if one of the engines suffers a catastrophic failure mid-takeoff. One of the greatest operational hazards tied to reduced thrust departures is the potential for human data entry errors. Accidentally typing an incorrect assumed temperature or picking a flawed thrust rating could, theoretically, leave a departing aircraft with dangerously thin performance margins. To completely mitigate this risk, commercial air carriers enforce mandatory, rigorous cross-checking protocols on the flight deck. Both the captain and the first officer must independently calculate the performance data, double-check the runway parameters, and visually verify each entry made into the flight management computer before accepting their final departure clearance. Furthermore, next-generation jetliners like the Airbus A220 and the highly anticipated Boeing 777X come equipped with automated performance monitoring systems that continuously evaluate real-world acceleration against expected telemetry during the takeoff roll. If this system detects that the plane is accelerating abnormally slow, the crew is alerted and can safely abort the takeoff before crossing their critical decision speed. When it is all said and done, reduced thrust operations remain deeply woven into the fabric of global commercial aviation, precisely because they have proven to be exceptionally safe when managed with professionalism and precision.